Hello everyone. My name is Siddartha Shankar.
And myself, Vishwanath Kulkarni.
We are graduate students at the Department of Computer Science at University Colorado Boulder, and this is our final project for the course CSCI 5253 Data Center Scale Computing. Our project is an IoT data platform. So the presentation will be as follows. We go over the project goals, software components, architectural diagram, debugging and testing, and capabilities and the limitations of the system, and then the learning outcomes. So going over the project goals, our aim was to develop a platform for the users to upload huge amount of IoT device data and also analyze the same. We also had a goal to provide a simple and user-friendly interface for the user to view the IoT device data and also some of the analysis. We also plan to achieve this by implementing a modular microservice architecture where each and every microservice is completely independent in carrying out its functions.
Our IoT data platform performs the following function. The user will have the ability to publish the data to the platform via APIs. Data will be stored in persistent manner. After the data is obtained, analysis of this data can be done by the user using our platform via graphs and the tabular view. There is also a logging module which helps in testing and debugging of the system. Initially, all the modules were containerized into Dockers. These images were then pushed to Google Docker imagery repository, following which a Kubernetes 3-node clusters was created. We then deployed the Docker images as pods in the cluster and also configured these pods to scale automatically based on the incoming traffic. We also exposed the endpoints for the data service pod and the IoT UI pod so that they are accessible over the internet. We have created Flask, which is a REST server which handles all the API requests. We have used RabbitMQ, which is the messaging service which transfers data between the pods and also ensures data integrity. We have used MySQL as a backend database for storing the IoT data. This was chosen because it enforces ACID properties and stores data in a persistent manner. We have used Redis to provide, which provides key value pair in-memory storage of the data, which helps in logging and the debugging of the system. And we have used Django for our website, which allows users to weave the data in tabular form and in the graphical view.
So going over the architectural diagram, initially a user accesses the platform via the respective URL provided. The front end for the user is implemented using Django and deployed in the Kubernetes cluster as a separate pod. The service is internally connected to a data service pod. The data service pod is basically the core of our system, which implements the Flask server and it handles all the API requests. This pod is internally connected to the RabbitMQ pod, which runs the RabbitMQ broker and which runs two topic exchanges, one for passing the IoT device to the SQL worker, which in turn stores the data in the MySQL database, and the other, which is connected to the Logger IoT pod, which stores the log data in the Redis database. These two databases, that is Redis and MySQL, are also connected to the data service pod, which basically helps in retrieving the data from the database and for displaying in the front end via APIs, which are implemented in the data service pod.
Let's go over the REST endpoints. We have exposed API endpoints which allow users to onboard themselves and publish their IoT data to us. We have 4 endpoints for the users. The first one being add users. Add users endpoint is for onboarding users and assigning an encoded user ID for them. User will then have to configure their IoT devices with assigned user ID to publish data to our platform. There are get data endpoints which allow users to get their data in a single go, or if they want from the starting index, they can do that by starting index endpoint. We have provided 3 endpoints for the Django UI, which helps users to view and analyze their system, which we'll go over in the next slides.
Coming to the debugging and the testing, so we implemented a modular logging module which basically stores all the logging information in the Redis database. This is done by storing the log data in the form of a key value pair, where the key is a timestamp at which the log was added, and the value is the log data, which basically stores the information such as from which IP address the request is arriving, what time the request arrived, the type of HTTP method. of the request, and then the URL of the request, and the HTTP status codes as well, and then the whether the request was successful or not. And it also stores the data of how big the particular request was, the size of the request. And we have provided a UI for displaying the logs to the user in the front end. And log analysis can be done both by the testers and the developers for from the UI itself. So coming to the testing, there are two types of testing that was done. One is the unit testing, where we tested each and every module independently and ensured that they are carrying out their functions as expected. And we also performed integration testing, where the modules were integrated, and then this we checked whether the system performed as expected. So basically, when we deployed all the pods for we did unit testing on the pods such as Redis, RabbitMQ, MySQL, and ensured that they were carrying out their functions independently and perfectly, and all the databases set up, etc. Integration testing was done when we integrated and connected the workers with these databases to check and make sure that the whole system is working as expected.
Let's go over the capabilities of the system. The IoT data platform has been designed to scale up when facing immense amount of traffic. So we have set up our system such that it can handle more than 200 to 300 customers concurrently. Efficient communication of the data via APIs. This has been achieved using Flask server, which allows users to onboard themselves and publish their IoT data to us. Persistent storage of the IoT device data in the MySQL database is achieved with the asset properties enforced. Logging module stores the log information for testing and debugging purposes. Let's go over the limitations, which are only few. We would like to mention them. First one is a possible loss of log data due to Redis. Sometimes what happens is that Redis pods might even crash, which will destroy the log data. Due to RabbitMQ enforcing data integrity strictly, there is acceptable limit on the number of concurrent users. This will limit our concurrent users to only 200 to 300 because of this limitation. Exact configurations of IoT devices are required, because if user doesn't configure their IoT devices without their user ID, then the data might be lost from the user end.
Now let's go over the working of the system. So initially we have deployed the said number of pods in the Kubernetes cluster, the data service pod, which basically implements the Flask server for handling the APIs, IoT UI, which is basically the Django pod, which is rendering our front end, the logger IT, which stores the logger information in the backend Redis database, MySQL database, which basically stores the IoT device data, RabbitMQ pod, which basically transfers the messages from the data service pod to the SQL worker and logger IoT pod, Redis database, which is used for storing the logger information, and the SQL worker pod, which is basically used for storing the data in the MySQL database. So when the user accesses the particular endpoint of Django endpoint to view the data using the particular user encoded user ID provided to him. This is the tabular view of the data where he gets, which he gets, and at a time he is able to view 7 of the records from the data. Moving on to the graph data. So when the user goes to the graph endpoint, he will be getting this particular graph data which he can view. So here we list the amount of power the graph basically tells us the amount of power which is being utilized by the small appliances, big appliances, and the rooms in the particular house. And it also gives us information about how much power is generated from solar and other resources in the present in the house. So moving on to the logs information in the front end, a user is able to view his logs. Here he gets the complete information along with the timestamp at which the log was stored, and the timestamp at which the request was arrived, and the type of the request, that is post for inserting the data and get for getting the data and getting the graph data, etc., etc., and along with the HTTP codes and the size of the particular request. So this is the basic simple UI, which a simple and user friendly UI which the user has access to in order to view his IoT device data. So in the end, what did we learn from this particular project? So we had a hands-on and real-time implementation of a microservice architecture, and we understood how each and every microservice can be implemented independently without being reliant on other pods for its core purposes, how Kubernetes makes deployment and scalability so easy, and it's a very simple task, and we won't have to worry much about connecting the VMs and etc etc, and how the pods communicate within the cluster regardless of the node or the VM on which they are deployed on, and how to manage a large amount of data. So obviously when we are getting the IoT device information from so many IoT devices in the house, how to store this data and how to retrieve this data from the database without the whole system crashing, because if you have to retrieve the whole say 200,000 rows at one point of time, so that's a big overload on the data, and how to manage this we learn from that as well. Importance of the logging module during testing and development phase. Without the logging information and then without the right logs of where we were going wrong, I'm pretty sure we this project wouldn't have gone so well, and we couldn't have completed it on time. So the logging module helped us a lot, and we also learned about the pros and cons of different database systems, such as Redis, where it's an in-memory database, and how if there's a system failure, then there is a possible loss of log information as well. So these were the learning outcomes of our project, and that's about it. Thank you.
Thank you.